because we are okay, good. Okay, so again, thanks everyone. So introduce the speaker of today, Katie Reeves. Reeves is the senior astrophysicist at the CFA. Her research focuses on two main connected topics. First one is thermal energy transport during solar eruptions, and second one is the magnetic reconnection processes that drive eruptions. She's currently the West Project Scientist of the X-ray telescope on the Coronal mission, and so the PI proposal submitted to the NASA Physics MAGIXS call to be the ECCO with three. We're going to be the top topic today, and that is the EUV coronal mass ejection coronal connectivity observatory. So in particular, the topic of today is the CME and Coronal Connectivity Observatory. And with that, Katie, thank you so much. Okay, so
It's the old.
the microphone is off.
You
I think so, yes. Thank you.
go pointer, by the way.
Mounted best.
Okay. Oh, sure. Because
The Dell.
for the
Yes.
I'm gonna do the computer.
Yes. Okay. So I'll
Right.
come now.
How's that for
Better?
sound? Is that okay?
Let's start with this.
All right, great. We'll do it that way. Okay,
Okay.
so
Sorry for the
no worries.
convenience.
Start again. Okay, good. Okay, so I'm going to tell you about ECHO. Oh, I forgot to share the screen. We'll get there, folks. We'll get there. Technology, it's great. Okay, share the screen. Share. Okay, yes, good, good. All right, great. What is ECHO? So as Federico mentioned, ECHO is the Extreme Ultraviolet Coronal Mass Ejection and Coronal Connectivity Observatory. There are 3 instruments on board observing the sun. The first is the ECHO Imager, which is a normal incidence EUV imaging telescope. It observes the EUV corona out to about 3.3 solar radii with a 3.1 arcsecond pixel resolution. The other 2 instruments are a pair of spectrographs. They're identical slitless imaging spectrographs, and they operate in 2 channels, a long wavelength channel and a short wavelength channel. So I'll tell you more about the instrumentation in a second, but first I want to ask the question, why are we doing this? Why ECHO? So this is the sun as we normally observe it from space. So we have EUV observations from, say, SDO AIA, a few other missions. We also have white light coronagraph observations from LASCO, Stereo, other instruments. And you'll notice there's a gap, right? Now, this gap isn't totally unobserved. There are white light coronagraphs from the ground that make observations in this gap, but only for a few hours a day. UVCS, which was an instrument on SOHO and built at SAO, observed this region with a slit spectrometer out to various heights. But there haven't been continuous 24-hour uniform observations of this region. So we've termed this region the middle corona from 1.5 to 3 our sun. And it turns out, turns out that a lot of stuff happens in this region. So on the solar wind side, this is where the solar wind is accelerated. This is where there's a transition from closed magnetic field to open magnetic field. On the eruption side, this is where we get the peak acceleration of CMEs. It's also where the flare reconnection, flare CME reconnection is happening. So there's a lot of interesting phenomena happening in this region. And it turns out you can see the corona out to 3R sun in the EUV. Now, this is kind of a surprise. This was a little unexpected because the EUV emission low down in the corona is collisional, falls off as density squared, and nobody expected to really be able to see the corona that far out. Turns out you can. This is an image from GOES SUVI. And this is stitched together from off-point observations where SUVI will point off the center of the sun on either side and take observations. Now, I should point out that this instrument is not made to do these observations. It doesn't have the sensitivity to really see stuff out in the middle corona, but yet we still see stuff. And not only do we see stuff, but we see stuff that is structured and dynamic. There's all kinds of things happening in this movie. And this isn't even a particularly active sun. These very bright spots are active regions, which are the regions above sunspots. You can see there are a couple, but not super a lot of them. So who knows what'll happen when the sun gets really active. So we're gonna fill this gap. We're gonna address two science goals, and those are to understand the sources, release, and acceleration of the solar wind close to the sun, and also to understand the symbiotic relationship between eruptive solar events and the large-scale corona structure. Now, if you've ever been involved in a big mission proposal before, you know every goal has objectives. So here are our objectives for the first goal. And I'm not going to read through all of these, but I will go through them one by one and talk a little bit about the science behind each of these. So the first objective is to determine the topological relationship between the global corona and the solar wind outflow. This is a series of images from the AIA telescope on the Solar Dynamics Observatory, and it shows interchange reconnection, which is reconnection between closed loops and neighboring open fields. And this is happening uncharacteristically low in the corona. Usually this phenomena happens a little bit higher in that gap. And so with the large field of view, ECCO is going to fully characterize the evolution of closed to open fields over long timescales. And it will give an unprecedented view of the corona's connection to the outer corona, the heliosphere, and the topological role in shaping the solar wind outflow. The next objective is to determine how the plasma properties of the middle corona govern the early evolution of the solar wind. So this is from a recent paper by Nora Ralphie, and they hypothesize in this paper that the solar wind is driven by lots of little jetting actions that happen on the surface of the sun. And this is a composite image of an AIA, and again, a SUVI is the outer image. And all of this fine structure you can see low down has counterparts further out. And again, SUVI wasn't built to do this, so the sensitivity isn't as good as you'd want it to be. But there's lots of information that we can pull. And ECCO is going to provide plasma diagnostics in nascent solar wind flows that are required to determine between solar wind models and that we need for comparison with in situ observations. The third objective under this goal is to determine the effects of active region energy buildup on topological restructuring of the corona from the disk to the middle corona. This is a series of images that shows an emerging active region in the X-rays from Hinode XRT. And with our observations plus the MHD models, we'll be able to assess the energy injection into the global corona as this flux emergence happens. And there's been some hypotheses that this flux emergence is supplying the energy that powers the slow solar wind. So we'll be able to test that hypothesis. All right, on to eruptions. So these are our three eruptions objectives. The first one is to determine how the characteristics of the global solar corona lead to and influence the evolution of eruptions. Again, this is another SUVI off-point observation. This is a more active sun, and you can see lots of eruptions happening as the sun rotates around. And what we'll be able to do is provide observations of changes in global connectivity that drive eruptions. There was a recent paper by Dan Seaton where he showed that an eruption seemed to be triggered by flows from above in the corona. And that's a triggering mechanism that was not previously thought of. And so we don't know if it was just that one observation observed by Dan and that was a fluke, or how often that happens. The next objective is to understand how and where the hot plasma is released and accelerated during the main acceleration phase of solar eruptions. So this is from a model by Chengxai Shen, and he did a flare model where he looked at the termination shock and these things we call super arcade downflows, which are these dark fingers that show up in hot plasma above flare arcades. And he found that the termination shock was actually above the super arcade downflows. This is somewhat controversial. This is a new idea, and previously people thought that the termination shock was below these super arcade downflows. So on the left there is the simulated AIA emission from Chengxai's model, and the AIA observation in the middle, so you can see how well they match. And then ECCO simulated, which I spelled with not enough C's. The simulated ECCO is on the right there, and that shows that we will be able to see these signatures of the termination shocks above the super arcade downflows with the sensitivity of ECCO. So we'll be able to observe the hot plasma that's associated with magnetic reconnection, and that will help us determine how eruptions are energized and differentiate between some of these different models of flares and CMEs. And then finally, we're going to look at shocks generated by coronal mass ejections. We're going to characterize these shock structures and the effects on the global corona. That picture, I mixed up my left and right. The picture on the left is a SUV image, and the picture on the right, sorry about that, is a LOFAR image of a type 2 burst. So that's indicative of a shock right in that region where we have a gap. So the ECCO wide field of view will provide a systematic survey of CME shock structures. And there's a hypothesis that the 1.2 to 3 R sun region is really favorable for shock formation. And we're going to test that hypothesis and also provide geometric parameters that are useful for shock models. Okay, how are we going to do this? This is our imager. It's a Cassegrain telescope with some filters, so we can select for 2 different channels, and a CCD that we are modifying from the Punch SMEX CCD. These are the 2 channels. We have a short channel, which goes from 126 to 138 angstroms, and a long channel from 171 to 218 angstroms. And what I'm plotting here is the effective area in black. That's the curve. The colored curves are the SUV effective areas, so you can see how much better we're doing than SUV. So SUV can see the middle corona, ECCO should be able to see the middle corona. And the underlying spectrum shows you some of the important lines that are encompassed by this effective area. So for the short channel, I've shown a flare spectrum. We get lines of iron 20, 21, 22. And in the long channel, you get kind of everything from iron 9 to iron 14. This is a simulated CME modeled by our friends at Predictive Science Incorporated. And we've simulated the emission through the short channel imager and the long channel imager to get an idea of what the images would look like. And that circle that I've drawn there is a circle at 3 solar radii. This is the imaging spectrograph. It's a prime focus reflective grating spectrometer. We have the same camera on the end and the same filter wheel so that we will select the same channels. These are the emissivities of the lines that we will see in the spectrograph. So you can see it's got quite a good temperature coverage. The dotted lines are the lines from the short channel, and the solid lines are the lines from the long channel. And this is what the data will look like. We're calling these things overlappograms. So if you're familiar with, say, Skylab observations, they did this with Skylab. We're going to do it with much better sensitivity and not on film. This is that same CME that I was showing in the imager channel, except we've rotated the sun so that south is to the left. And the CME structure comes off separated by wavelength. So what we get is a series of overlapping, spectrally pure images of the sun and the structures having to do with the CME. So these are the same passbands as the imager, more or less. The long channel is a little bit shorter because of the size of the CCD and the amount we spread the overlapographs out, but they're very similar. So for the hot channel, we get iron 20, 21, 22. And then for the long channel, we get that same series of iron lines, except we can't really get the iron 14 anymore. We also get hot lines for the long channel in flares, calcium 17 and iron 24. So what this allows us to do is easy spectroscopy of compact regions. So if we have like an active region, or even better, a flare that's very compact, we can just pick off those pixels off the CCD, and we've got an idea of the lines. So this is an example. This is a cutout of the imager over on the top left. And then this is a cutout of the central portion of the CCD for the overlapographs, the overlapogram on the right. And the little box is the active region that we've plotted on the bottom in a variety of different lines. So you can see how things look different in the different iron lines from iron 9 all the way up to iron 13. Now, sometimes you're going to want to look at larger, more extended structures. And so how do you deal with that? Well, it turns out we have a technique for unfolding the overlapograms into their constituent ions. So this is from a paper written by Amy Weinberger in 2019. And she was using a previous version of this telescope called COSY. And what I'm showing here on the left is the true emission measure from a MHD model. And then we ran that all through the telescope response functions and gave it to Amy, and she inverted it. And then on the right side, you see the inverted emission measure from her algorithm. Pretty good. And then this image shows several ions in two ions, iron 12 and iron 13. And you can take those and make ratios and do density maps. So the top is the true from the MHD model, and the bottom row is the inverted using the unfolding algorithm. So this works pretty well. We have done it with ECCO. So here are a couple of time steps from that same CME simulation I was showing before, and I just picked out a couple of ions. So on the left, we have iron 8, which is from the short channel. On the right, we have iron 13, which is from the long channel. And the top is the first time step, and the bottom is the second time step, which is the same time step that I've been showing in the other overlapograms and in the imager. So the trick to this is, because you have so many lines in that EUV passband, you get repeated information across the detector at different levels of overlap. And that's the key to creating extremely reliable inversions. So the unfolding algorithm is proven, and it's fast, and it's robust. Okay, so we can do this with simulated echo data. Can we do it with real data? Yes, yes, we can. So this is from the MAGIXS rocket flight. This is the Marshall Grazing Incidence X-ray spectrometer. And this was a sounding rocket experiment that launched in July 30th, 2021. MAGIXS is a spectrometer with a wide slot instead of a narrow slit. So it produces these overlapping spectra, very similar to what ECHO will do. The picture on the left there is an XRT full sun image from around the same time as the rocket flight. And the MAGIXS position of the MAGIXS slot, the approximate position of the MAGIXS slot is shown by the rectangle. The spectrum is down here in the bottom, and all of the lines that MAGIXS picks up are marked in different colors, and they're all kind of overlapped, you know, especially like, say, the iron, what is that, 8 and iron 7 are pretty overlapped. But we have another bunch of lines of iron 7, so that's good because that helps us unoverlap things. So these are all overlapped, but we can apply the algorithm and get these spectrally pure images of different ions at that location in space. So this is this image up here, this portion of the sun, and this top portion of the spectrum here that we're unfolding. So you can totally do it. All right, so we know we can deal with the data. We know the data is going to be great for science. And now we have to figure out how to put it in space because you can't observe the EUV from the ground. So our friends at Ball designed this spacecraft for us. You've got the Echo Eye aperture and the spectrometers. Let's see if I can, here we go. So this is the imager here. These two guys are the spectrometer, spectrographs. And then we have a flare sensor that'll help us flip into a different mode for flare observations. I'll talk about that in a second. And then we have the high frequency sun sensor here, which keeps us pointed at the sun. And then this is a side view. The sun is off to the bottom here. So these are the fronts of the telescopes. You can kind of see how the whole observatory fits together. We're going to put it in a sun synchronous orbit, and the sun synchronous orbit will be aligned with the terminator. What that means is that we're able to point at the sun almost all of the time. There is an eclipse season, which will be either in summer or winter, depending on which LTAN we use. We're right now aiming for an eclipse season in the summer, but we'll see when we actually end up launching. And these are our observing modes. So we want to be able to observe both quiet sun targets for the solar wind science, and also flares and CMEs for the eruption science. So during the normal mode, which is when we'll mostly be observing quiet sun, we're going to take multiple images and then sum them to increase our sensitivity. And with that summing, we'll get an image with a 54-second cadence. We'll also put images into a flare buffer so that we can save them in case a flare happens. And in the case of a flare trigger, all of the images in the flare buffer are downloaded. We'll have this flare sensor on board. It's a X-ray detector, and it'll detect X-ray flux. When that flux hits about a GOES M1 level, then the trigger will go off and we'll go into flare mode. And flare mode will take high cadence images with the imager and we'll do long and short exposures with the overlappograms to get both the flare stuff, the flare spectra, and also more extended but fainter structures like the CME. And then when we hit another threshold, which we've marked as C1, we'll end the flare trigger, and then we'll go into CME tracking mode. And here we'll take long exposure time images, and again, long and short exposure overlappograms to track that CME as it leaves the sun. And then we'll go back into normal mode and go back to doing our quiet sun science. So the ECCO CCDs are rectangular. They have 4,000 pixels in the horizontal direction and 2,000 in the vertical direction. In normal and flare modes, the imager is just going to return the central portion of the CCD, so it'll be a square that gives a field of view of plus or minus 3 R sun. But CME tracking mode will feature images with a field of view of 6.6 R sun in the horizontal direction. So we will be able to see CMEs that go further out. And this is a discovery space. There is this one paper from Solar Orbiter where the FSI on Solar Orbiter imaged a CME in 304 angstroms out to almost 7 R sun. So that particular CME is probably going in the wrong direction, since our horizontal direction would be, or our long direction would be in the horizontal direction. But nevertheless, it seems likely that we will see stuff out even further than the 3.3 R sun that we normally image in. This is the science team. We consist of a big team here at the CFA. Giulio Delzana from University of Cambridge. We have several co-Is, and we coordinate closely with folks at the Southwest Research Institute. Amy Weinberger at NASA Marshall is responsible for the unfolding algorithm, and she and Sabrina Savage are co-Is. And then Predictive Science does our MHD modeling, and Wei Lu at Barry Lockheed Martin is a science co-I working on eruptions. Here's the timeline. We submitted our SMEX proposal December 8th. We have a down select in June of 2023. Then we are selected. Phase A starts in July of 2023. There's another down select in September 2024. And then phase B begins fall 2024, and launch would be at the end of 2028. And this is actually really good for us because it'll be the downside of the current solar cycle. That's when you tend to get lots of really, really big eruptions, and then going into a quieter period after solar maximum will be a good time to do our solar wind, more quiet sun science. So I didn't need a time warning, so that's all I have to say.
Thank you so much.
2-year time quiz. Yeah, Mike just asked what the how long the mission was, and it's a 2-year prime mission.
Other questions from people here?
Keep flares, you get your flare buffer day or so. Limit how many you can get down.
Yes. I mean, we did this math, and now I'm forgetting the number off the top of my head, but yeah, we looked at the previous 2 solar cycles, and we tuned our max data rate to allow us to catch multiple flares even on the busiest day. So Ed's the data rate guy, so maybe he remembers.
5 a day, and 20% of the local time spent in what I think is good. Because that's what we use to source the data model.
That's a great algorithm. I wondered if anyone tried applying it to the Chandra rating data and supernova remnants that show very similar.
Ooh, I don't know. That's a good idea.
And I think it's been a real challenge to get anything out of it.
Yeah, yeah. We should talk to Amy about that.
I think it's a very cool idea. Are you going to be able to get mass estimates of the CME?
No, with the white light chronographs, because it's Thomson scattering and you're seeing everything, you can get mass estimates. But that's a little harder in the EUV because you're selecting out particular temperature ranges. So yeah, we can't do like the more direct measurements like the white light chronographs can do.
Well, no, I think it's better follow back.
Any other question? Any question online? No?
I hope that this isn't too inside baseball. What are the implications of the super arcade downflows being above or below the termination chart?
So it's whether or not the super arcade downflows are part of the flare reconnection or not. If they're below the termination shock, they are not part of the flare reconnection. If they are above the termination shock, they are more likely to be part of the reconnection process that's powering the flare. People have hypothesized that these things are actually reconnection outflows. If they're below the termination shock, they're not reconnection outflows. Yeah. So the Cheng Sai's paper says that they are actually an instability in this interface region between the termination shock and the flare loops. It's like similar to the like a instability that you get in supernova, actually. So fluid instability.
Small practical question. Isn't this orbit overcrowded by spice elements?
I don't know. Where's Jonathan McDowell when you really need him?
That's where all of them are.
I mean, it's where we always put the solar satellites too, because it's a great place to look at the sun.
Yeah. There are as many solar satellites, as many.
Yeah,
satellites.
yeah. I don't know. I would have to ask Jonathan about that.
Any more questions from here? No. Online? No. Okay, let's thank Katie again. Thank you very much.
So my question had been related to what Martin